Good afternoon, Panthers. This is Dr. Augustine, and I am going to talk to you today about weak acids being titrated by strong bases or weak base strong acid titrations. They're both basically the same type thing. They're just sort of inverse of one another. This is still covering chapter 17.4 intro. It's part 3 of a 4-part video series, and I do have to warn you, this is probably going to be the most intense of all 4 of these videos. There's a lot of calculations involved, and you got to kind of hang with me on this. So just like the last video, we're going to calculate how to calculate every point along a theoretical titration curve for a weak acid strong base titration. And again, just like the last video, you can use the same reasoning for weak base strong acid titration. It just involves POH instead of pH if the curve is inverted. So we're going to break down this strong acid, strong base titration curve into 4 different regions, and then we're going to show how to do the different calculations. There is an example problem that shows several different places on the curve. If you can do all the places on the sample problem, you are in really good shape on this, and I've done a similar thing for the strong acid, strong base case. All right, before we dive into the actual titration curve, let's just make a quick refresher on a buffer situation. So remember, a buffer is when you have a mixture of a weak acid or weak base and its conjugate acid or base. If we have in solution a mixture of those two things, we create what's called a buffer solution. This picture's from your book. This is ammonia, which is a weak base, and ammonium chloride, which is a weak acid. The actual weak acid part is NH4 plus. So when we combine those two things together, the NH4 plus and the NH3, that forms a buffer solution. When we have those two guys together, we have created what is known as a buffer solution. And remember what a buffer solution does. A buffer solution resists the change in pH. So we can either add acid or base to it, and the pH does not change very much. So before we dive into the nitty-gritty details of the titration curve, let's just quickly refresh ourselves about the equations that we use to solve a buffer solution. So remember, let's say we have a typical buffer reaction, HA, the weak acid, plus water yields H3O plus A minus, and these should all be aqueous. Okay, and remember we can use the equilibrium expression Ka to tell us the strength of an acid is equal to the H3O plus concentration times the conjugate base concentration divided by the weak acid concentration. All right, and if we want to find the pH of this solution, remember the pH is negative log of the H3O plus concentration. So I need to isolate H3O plus, and I will bring that over to the other side. So we'll say concentration of H3O plus is equal to Ka times the concentration of HA divided by A minus. And I am going to take the negative log of both sides of this equation. So I have the negative log of H3O plus equal to minus log of Ka times concentration of HA divided by A minus. Recall from your properties of logarithms, the log of A plus A times B is equal to the log of A plus log of B. All right, so this is going to be negative log H3O plus is equal to negative log of Ka minus the log of the concentration of HA divided by A minus. Okay. Now, negative log of H3O plus, that is pH, equals to negative log of Ka, that's the pKa, and minus log of A minus HA over A minus, another property of logs, negative log of A divided by B is equal to the plus log of B divided by A. So we're just going to flip this around. pH equals to pKa plus the log of A minus divided by HA. This equation is going to be your best friend in any type of buffer reaction. This is called the Henderson-Hassenbach equation. And we've got three things in this equation. We've got pH, we've got pKa, and we've got a ratio of our weak acid and weak base concentration. So if you have the Henderson-Hassenbach equation, you can find out anything you want about a buffer region of a reaction. And we are going to need this because we end up with a buffer region when we do an acid-base titration with a weak acid and a strong base, or a weak base and a strong acid. Couple of other things to note, which your professor may not have noted. Look at this second term here. This ratio term is what determines how the pH varies. And if you notice, it's a concentration of the conjugate base divided by its conjugate acid. If you think about that, if we write this in terms of units, we have log number of moles of A minus divided by volume divided by number of moles of HA divided by volume. In this buffer solution, the volume's the same, right? If we have a solution made up of some combination of these things, we have the same number of liters in the same solution. It's a uniform solution. So therefore, we can either use concentrations or we can also use number of moles. And this is going to be really helpful when we do these titration type reactions, okay? So let me just summarize what I'm saying here. You can either use concentration in the Henderson-Hassenbach equation, or you can use number of moles, which is really convenient for doing these types of reaction. So before we actually dive into a titration reaction, I just want you to be aware this equation is going to be our best friend. We're going to use this for basically half of the pH curve. And if you know how to use the Henderson-Hassenbach equation, you've got a lot of the tricky stuff already done. And we're actually going to usually use number of moles rather than concentration because it saves us the time of having to calculate the concentration. We can use a mole table to figure out the number of moles, and we can find the pH. So I'm gonna move back, erase all this, leave the Henderson-Hassenbach equation on, and we'll take a look at some of these reactions. All right, so before we get into the nitty-gritty of actually doing these calculations, just like in the strong acid, strong base calculation, I want to point out that there are several unique regions. So the first region is when we have no base added. Volume of base is 0. In other words, that's that very first data point that you have on the graph. That is actually the exact same calculation that you had to do in section 16.6 of your book. I'm gonna give you an example of this, but basically it is you have a certain concentration acid and you have a certain concentration Ka, and you want to find out what the pH is. In other words, I have not added any base, and I'm just trying to find out what this pH is based on the fact that it's a certain type of acid. So we're going to do an example problem where we plot several things along here. First point, though, is you've already learned how to do section 16.6. Second region along the pH curve. Once you add the slightest amount of base all the way up to just below the equivalence point, you have created a buffer region, which is why I started out writing about the Henderson-Hassenbach equation. So anything in this region, you're going to want to use the Henderson-Hassenbach equation. And we're going to use a mole table to find out how much HA and how much A minus we have after the chemical reaction is over. And we're going to plug them into the Henderson-Hassenbach equation, except this log term is going to be log number of moles of A minus divided by the number of moles of HA. Okay, that's going to be in this region 2 of the titration curve. Region 3 of the titration curve is going to be at the equivalence point. And at the equivalence point, we're going to have to do another equilibrium calculation. Because the only thing we have remaining is conjugate base at this point. I'll show this to you in a chemical reaction. And then beyond region 3, so from just a little bit of the equivalence point past, this is actually an excess reagent problem. So we have excess OH minus in this particular case. Excess OH minus exists beyond the equivalence point. So just like in the acid-base case, we have 4 different distinct regions, except unlike in the acid-base case, we have this buffer region right here, which is not the same as the strong acid, strong base case. Okay, we're gonna have an initial point, which is just like you did in 16.6. We're gonna have a buffer region that goes from when we first add something all the way up to just below the equivalence point. At the equivalence point, we're actually gonna have to do another equilibrium calculation because all we have remaining is the weak conjugate base in solution. And then beyond that, as soon as we start adding excess base, we're gonna have excess OH minus, and we're gonna use POH to calculate the pH of our system. Okay, again, before we dive into the details, because it could get really easy to get lost in the details of this, I want to quickly point out everything we're saying here also holds for the case of a weak base and a strong acid. Okay, in this case, we'd have volume acid, and we would have pH on the y-axis again, and we'd get some kind of curve that looks like this. So it's essentially a mirror image of the weak acid, strong base case. It's just going to be flipped around, and we're going to have the buffer region is now going to be on the high pH side. So pH is going to be around, like pH 7 would be here, let's say. So the buffer region is going to be a higher pH than 7. It's going to be a conjugate base, conjugate acid region as you're titrating it. Okay, so the buffer region is going to be on top. Equivalence point is going to be here. The other thing you should note, we should note this on both of them, the equivalence point is actually higher than 7, which I'm also going to point out. And in this case, the equivalence point is going to be less than 7 in a weak base, strong acid case, and then it's going to saturate out at a higher value once you get past the equivalence point. All right, so just for the sake of completeness, I'm going to sketch in an equivalence point here, which is going to be a lower pH than 7. This equivalence point is a higher pH than 7. So weak acid, strong base, higher equivalence point than 7. Weak base, strong acid, lower equivalence point than 7. I'm looking at the time, we're already at 12 minutes, so what I'm going to do is I'm going to break this up into a couple more videos and break down each particular section. So here's a preview of what's coming. Before we get into those videos, this is the problem we're going to work on. And this takes into account all 4 different sections. And I also notice there's a little typo in here. So the problem is calculate the pH during the titration of 40 milliliters of a 0.100 molar should be propanoic acid. Your notes are corrected. Here's the Ka for this, and the shorthand notation is just HPR. After each of the following additions of 0.100 molar sodium hydroxide. So we got a couple different solutions. We got 0 milliliters, that's the beginning of the curve, 30 milliliters somewhere in this region, 40 milliliters at the equivalence point, and 50 milliliters beyond the equivalence point. Note these values do not correspond to this picture. It's a different titration, but there's 4 different regions. We're going to do 4 different calculations for this problem. So check out the next videos with the details of this actual problem set.